Okay. So we discussed in the previous class how to, or in the previous classes rather, how to calculate the internal forces and reaction forces for any determinate system, right? So that may include a frame, a beam, or a truss. Okay, so you can calculate the internal forces. Internal forces you can calculate directly by using equilibrium. So you just to make sure that every part or every component of the entire structure is in equilibrium. So all the forces are balanced, and as long as that is taken care of, you can calculate the internal forces everywhere. Fine. After calculation of the internal forces, then comes the question of calculating deflections. Okay. So again, for determinate systems, we discussed a few methods to calculate the deflections. Right? So as long as you know the internal forces, many of these methods would work. So some of the methods that we had used, one was double integration, then there was one derivative of double integration. What is the name of that method? Anybody? There was a kind of a derivation or derivative of double integration method. So it was an like for beams, it could be used. It is, can hear me, right? Everyone? There was a method that is actually an outcome of the double integration method, but that makes the calculations much simpler, especially in particular conditions. Moment area method.
Magauli's method, sir.
Which one?
Nicholas methods.
Magauli's method.
Macaulay methods.
Macaulay method. Okay, I mean, probably you guys are calling the same method by different names. I call it moment area method. I'm not sure if it is like Macaulay method could also be another method. I don't know. So the one that we discussed in this class is was the the moment area method. Okay, and I find that method to be very powerful, especially if you have a moment fixity at any point in the member, or if you have a symmetry anywhere in the member. So whenever you have these kind of situations, you know that the slope is going to be 0 at that location, and that makes the life much simpler and calculation of deflections very easy, especially for simpler loads. Okay, so that is one method, double integration and moment area method. And the other method that we discussed was virtual work method. Okay, so again, there are other methods for energy-based methods, but I prefer the virtual work method. This is pretty universal and can be applied in almost any condition. Okay, so and using one of those methods, we could solve any determinate system. We can calculate deflections in any determinate system. Okay, so for trusses, we saw that energy-based methods are much more powerful than any other method. So mostly it is not even taught in classrooms how to calculate deflections of trusses other than energy principles. Okay, because otherwise doing that geometric compatibility becomes a major issue, major challenge. So okay, so we will move forward now to solving some of the indeterminate, some methods for solving indeterminate systems. The first one we will start with is flexibility method. Now, some discussion I wanted to present between flexibility method and force method. Sorry, flexibility method and stiffness method. So flexibility method is also known as force method, and the other method is stiffness method, is also known as displacement method. And we will see in a minute why is it the case. Now, we will again do a more detailed discussion on the comparison between flexibility method versus stiffness method. One important thing you should know here is that flexibility method is more fundamental method. Okay, it comes from the fundamental principles. However, so basically you use the basic concepts of solving a determinate system that we have developed already, that we have developed a good understanding of, and then on top of that we impose the compatibility conditions. However, the stiffness method, in order for you to use the stiffness method, you need to develop the formulations for individual elements, and those formulations have to come from the knowledge of flexibility method. So without the flexibility method, or without this algorithm of flexibility method or this protocol of flexibility method, you cannot even develop the formulation of stiffness method. Okay, so flexibility method in a way is inbuilt in the stiffness method, and that is something that we should be familiar with. So stiffness method is typically used by all your computer programs. So whether you are using Stat Pro or you are using SAP 2000 or um, even the more advanced programs like proper finite element analysis programs, also to some extent, they are also in a way built up around the flexibility method. Okay, wherein you have to develop a flexibility matrix, sorry, stiffness matrix. So they are built up around stiffness method. I misspoke. All these programs are built around stiffness method, and you have to prepare a stiffness matrix for that. Okay, so in the flexibility method, however, the problem is that it cannot be computerized very easily. Okay, because you need some intuition to decide which degrees of freedom to release. So can somebody quickly iterate for all of us, like tell us what are the steps in the flexibility method? So if I want to solve a indeterminate system using flexibility method, what steps should I follow? Maybe I can start asking individually. Sairaj, can you hear me?
Yes, sir. Yes, sir.
Yeah. Can you answer this question?
Yes,
What
sir.
steps would you follow to solve a system, an indeterminate system using flexibility method?
Sir, sir, first we find out the indeterminacy of the structure, sir.
Okay.
After finding the indeterminacy of the structure, according to that, we try to make it into a determinate structure by changing the configuration, sir. Like removing the means changing the support condition, or in a trust we remove one member.
Okay.
After that, we find out the reactions of the configuration, sir. After finding the reactions and the forces in the members, we try to form the flexibility matrix. From the flexibility matrix, we find the force, means we find the required reactions that are present, sir. Uh, that's it. Means this
Yeah.
is the process now.
Okay. Yeah, you almost covered everything. I feel like one crucial step, either you didn't say it clearly or I missed it. I don't know.
Sir,
Anybody else wants to try something here? Did you? Yeah, Asadullah, you want to say something?
Yes, sir. Actually, I missed only one thing, sir. That is compatibility equations. Based on compatibility equation.
Right.
Okay.
So compatibility we have to satisfy. So yeah, I mean, he explained that you have to turn the indeterminate system into a determinate system or a number of determinate systems. It does not have to be a single determinate system. Sometimes it may be more than one determinate system that you can break the big system into. And then on those determinate systems, you calculate the deflections or the rotations. So deflections in general term includes rotations. You calculate deflections at the locations where you had released the constraints. Okay, and and then you calculate those deflections, and those deflections obviously for any arbitrary value of or whatever the loads are given for those load values, those deflections will be violating the compatibility requirement. Okay, because you have released the force, so you have changed the structure, so therefore there will be a violation of compatibility, then or the violation of boundary conditions. So boundary conditions is also a special type of compatibility condition. So that violation then you have to correct. And how do you correct that violation? How do you fix that problem? You fix that problem by applying an unknown force or applying unknown forces in the degrees of freedom that were released or the constraints that were released. Fine. Okay, so maybe what I can say is that I'll say it's primarily 4 steps or 5 steps rather. Okay, the first step is to calculate the indeterminacy of the system. The second step would be to change the indeterminate system into a determinate system. The third step would be to solve the determinate system, the new determinate system, for 2 things. One, your loads that are given on the structure, external loads, real loads, known loads, and the second one would be wherever you had released the restraints to turn the indeterminate system into a determinate system, those restraints you apply unknown forces, okay, some arbitrary force, let's say M or R or whatever. You apply some forces there at those locations where you release the restraint, and you solve the system again. And when I say solve, you calculate the internal forces for all such cases. Okay, that is step 3. It has 2 parts. Then comes the step 4. In step 4, you calculate the deflections at those constraint positions that you had released. You calculate the deflections at those locations because of the external forces that are applied, that is real forces, and also because of the unknown restraint forces that you had released. Okay, and then make sure that the deflections that you get because of real forces, right, in those locations, and the deflections that you get because of unknown forces that you applied at those locations, the total deflections satisfy the compatibility condition. That means it does not violate the requirement that was. So like if the 2 points were touching each other in the indeterminate system, when you make this system determinate, you say that, okay, they are not touching each other, I've broken it here. So then because of the external load, these points can go into each other maybe. Okay, but then you apply some balancing force or some kind of unknown force to push these points away from each other again, and you so that forcing this displacement to be 0, and likewise you calculate by this process, you calculate that force required there. Okay, and that will give you the starting point for calculation of internal forces, and from that point onwards you can calculate internal forces everywhere. So step 4 was calculation of deflections everywhere. Step 5 would be forcing the compatibility condition. Okay, and as a result of forcing the compatibility conditions, you will get some internal forces. That is pretty much typically what you have to do. Sometimes you may be asked to solve the entire system finally. So for that, all you have to do is you have to go back to your step 3. In step 3, you had calculated internal forces for the known external loads and for the unknown restraint forces. But now those restraint forces are known. So you substitute those values in those internal force diagrams and you will get the final result. Okay, so what I'll do is instead of talking too much into theory, we will start with an example, and I think with an example it will be easier for us to follow. Okay, so second slide I'll skip. You all pretty much know what it is all about. So we will start with an example. So this is a fixed beam. You all already know what are the moments at the ends of a fixed beam that is loaded with a uniformly distributed load W. Do you know or not? Can anybody tell me what are the fixed end moments in such a beam?
W square by 12.
WL square divided by 12. What is the midspan moment?
WL square by 24.
WL square by 24. So typically this since you already know it, I'm just kind of putting the results before even starting to solve. So this is how a typical bending moment diagram will look like. This will be WL square by 12, and this one will be WL square by 24. Okay. If you add the two, WL square by 12 and WL square by 24, how much do you get? Ignore the sign, just add or take the difference from here to here. What is this distance? How much is that moment? Anybody? How much is it?
WL square by 8.
WL square by 8. You also appreciate this fact that if you have a simply supported beam, then the bending moment diagram looks like this. How much is that moment?
WL square by 8.
WL square by 8. So this WL square by 8 is same as this WL square by 8. Can you appreciate why? What does it mean? All it means is that you can simply, what am I doing here? If you see, I had a simply supported beam. I had applied uniformly distributed load on this. I got a bending moment diagram of this one, which had a WL square by 8 moment here. Okay, then I somehow fix it, right? But it was not actually a simply supported beam. It is a fixed beam in reality. I'm just starting point is simply supported, but it was actually a fixed beam. So what in a essence it does is that I'm applying some kind of a moment, and that moment turns out to be WL square by 12 in opposite direction, minus WL square by 12. It turns out to be this much bending moment in order to maintain the slope as 0. Okay, so let's say if I apply this moment, then what will be the bending moment diagram of this beam? Tension side positive, right? So this was downward, this one will be upward. Just top side is tension side. How much will it be? WL square by 12 in this direction. Now, if I simply add the two, what will I get? If I simply add the two, basically all these points will move up by WL square by 12. That's what I will get. This 0 will turn into WL square by 12. At mid span, it will be WL square by 12. Sorry, I meant 12 here. I'm sorry, this was WL square by 12. So in the mid span, it will be WL square by 12 minus WL square by 8, or other way around, WL square by 8 minus WL square by 12. And this one. So that's what you have, WL square by 24. Okay. Fine. You can understand this concept even further. Let's say I don't have a full fixity. Okay. If I don't have a full fixity, I have a spring here, let's say. I'm kind of digressing here, but that's also an important discussion, so I'm just covering it here. It should be discussed more rigorously in design courses, but we usually don't get so much of a time in a design course. So I was hoping to get a fixity, full fixity at both ends, but somehow I didn't get that for whatever reason. It's sometimes very difficult to get a full moment fixity, a very stiff moment fixity. So let's say I get something of this kind, which is stiff enough, but still has some flexibility, some rotational flexibility. So these joints, these ends can rotate a little. Okay. In that case, I will not be offering WL square by 12, but I may be offering WL square by 16 or WL square by 20 or something like that. So whatever moments you are applying at the ends, this bending moment diagram, full bending moment diagram, will shift by that much. So this time, if it is, let's say 20, so this one will be 1 by 8 minus 1 by 20, whatever that turns out to be. WL square, of course. Okay, so this has a very important concept in members which are allowed to yield. So for example, for extreme load conditions, often the members yield at the ends. Okay, so if they yield, what we do is that whatever is the yield moment capacity of the member, that much of moment is applied in the negative side. So on the positive side, only the balance is the demand. Okay, so if it is a fixed beam, let's say you are planning it to be a fixed beam, your moment demands were here. How much was the moment demand if it was a fixed beam? Okay, in negative, and the moment demand here would be WL square by 12, 8, sorry. No, sorry, 24. I'm sorry, by 24. Now, typically what happens is that, especially in steel, you can often go with a symmetric section, right? So its positive bending moment demand is, or capacity is very similar to its negative bending moment capacity. Okay, and if that is the case, this is not a very efficient way of designing it, because this beam has a very high negative moment demand. Okay, so in comparison to positive moment demand. So what I can do is I can take the average of the two. How much will be the average of the two? Or 1 by WL square by 16, right? Agreed? So if my beam's negative moment capacity is only WL square by 16, and I'm sure that it has enough ductility that it will deform but will not lose its capacity to resist WL square by 16. So that means if a hinge is forming at this point and the moment versus rotation behavior is of this kind, wherein it reaches WL square by 16, whatever load, and at around that point it yields, but then it continues to resist that load for a very large rotation instead of dipping it immediately. So it does not dip, it maintains. Okay, and if we are sure about that, and that can be assured by making the cross section more compact. Okay, so if we do that, if we make sure that the cross section is more compact, it does not undergo local buckling after a very large amount of yielding also. In that case, you can design the cross section to have a capacity of WL square by 16 on both sides, positive and negative. And then automatically what will happen is, as the load keeps increasing and this load reaches WL square by 16, not WL square by 12. As soon as it reaches WL square by 16, it starts to yield, and then any additional load that you apply will go into the positive side. Right? This will be WL square by 16. This can be WL square by 16. Okay, so this would be a more efficient design. You don't have to really design for whole WL square by 12 in the negative moment side. Okay. So sometimes this approach is adopted, or especially when you are dealing with very large forces. So then you are sure that the forces are going to be so large at the ends that my cross section is going to yield. I cannot avoid yielding here. So then still you can count on the residual positive moment demand. Okay, and the beam will not fail. But if you don't have any residual positive moment demand, let's say you design it in such a way so that your hinges are going to yield here, but here your capacity is only WL square by 24, then your beam will simply collapse. Okay, if the hinges form and you exceed the moment demand here also, then the beam will collapse. Okay, I think I digressed here a bit too far, and I don't know how many of you were able to follow it closely. This entire concept is called moment redistribution. Okay, moment redistribution, meaning that at the ends it was supposed to resist WL square by 24. Sorry, at the ends it is supposed to resist WL square by 12, and at the midspan it is supposed to resist WL square by 24. But if there is a yielding taking place at the ends, then that moment gets distributed to the midspan, redistributed to the midspan, and that is an acceptable design philosophy. Okay, it is practiced often. Okay. All right. So moving forward with our flexibility method of analysis, we have this fixed beam, and we will try to solve this and calculate the internal forces in this beam. So first, a quick recap. First, a few discussions on the application of moment area method. So I particularly am a fan of moment area method and virtual work method. It's basically everybody finds comfort in various different methods. So I find these two methods very effective. When we want to use moment area method, there is something that we often need. If you have a triangular bending moment diagram, okay, so this direction, let's say you have length L, and in this one it is M value here. It's a triangular bending moment diagram. In moment area method, we often need to calculate the area under the curve. Okay. And also we need to calculate the location of the centroid. So centroid location is calculated that in the horizontal axis direction, what is the centroid distance from one end. So we will call it X bar. Area we will call A, and centroid we will call X bar. So for a triangle, we all know area is ML divided by 2, and the centroid location will be how much? How much will be the x bar value?
2/3 of L.
2/3 of it.
2/3 of L. Fine. Now that is for a triangle. We often, whenever we have a distributed load, uniformly distributed load, we end up with a parabolic curve, right? So there are two types of parabolas possible. So, what is the D? One type of a parabola could be this one, okay, and this parabola is basically having zero slope when it meets the horizontal axis. The other type of parabola could be of this kind, or in other words, it is just the other side of this parabola. If you imagine this rectangle, so once I'm talking about drawing the concave side of it, the other time I'm taking the convex side of it. So both of them are parabolic. Quadratic. So in this kind of situation, you have to bear in mind that I am not calculating something here. I'm not talking about this area only. I'm not talking about only this area. What is important here is that we are covering up to the point where the slope is 0. At this point, the slope is 0. Okay. And in this case, at this point, the slope has to be 0. Fine. So unless that is true, you cannot use the current this information. So for such a case, area under this diagram will be equal to anybody?
1/3.
1/3. Let's say this is M and this is L.
ML.
ML. Okay. And the centroid x bar from here is how far?
3L/4.
Very good. 3/4. Sorry. 3/4. 3 divided by 4. Okay. For this case, the area will be, everybody should know now, the area will be complementary area of this case. Right? So that is 2/3 of ML. And X bar, even I need to recheck, I've forgotten. Does anybody remember how much is it? Is it
3 by 8.
3/8 of the L.
On the opposite side.
Is it from the other side?
5/8.
Ah,
Yeah,
5 by
there
8.
is slope
Yeah,
is 0.
correct. Yeah. So X bar will be 5/8. Okay. So these information you can always, like whenever in the exam you are required, you don't have to integrate all these parabolas to get the area and the location of the centroid. You can directly use this information. I won't mind. Okay. If you remember that, even if you don't remember it, you can keep it handy. Our textbook, Kibler's book, at least, gives a separate sheet wherein geometric properties of areas are given. So the first 4 parts: triangle, trapezoid, semi-parabola, parabolic spandrel, these are given to you. And then you can even get similar values for nth degree curve. So that is more generic formula that you can also use it if you need to. That you can use for cubes, etc. also. Anyway, so moving forward, now we had a problem in our hand. This was a fixed beam. So if you want to solve this beam, first step was, so let me first start with the problem. The length is L and it is supporting a distributed load W. Okay, so there can be 2-3 ways you can do it. One is, first you have to find the indeterminacy. Now I am saying that it is a beam. I'm stating that it's a beam. So if it's a beam, you can ignore the axial forces. Okay. Then basically what are you left with are only the vertical forces and the rotations or the moments. So moments and vertical forces. That means what is the degree of indeterminacy? Degree of static. Only one. Sure.
2.
The 2.
Yeah. So basically you can imagine that this is a simply supported beam. And on that top of simply supported beam, I have basically restrained. So in a simply supported beam, it was allowed to rotate at the ends, but those rotations have been restrained at each end. Therefore, 2. Or alternatively, you can think of it instead of a simply supported beam, you can say it was a cantilever. If it was a cantilever, it was allowed to move down and it was allowed to rotate here or move up. Just keeping the sign convention positive. So now both of them are restrained at this end now. So these two. Okay. And this movement was anyway disregarded when we considered it a beam. Okay. If we had called it a frame, then that movement would have been causing another degree of static indeterminacy. But in this case, we have only 2 because we are disregarding the axial deformations. Fine. So that is first step. The second step is to resolve this into a determinate system. Okay. So we can go with a simply supported beam, but the way I've done it in your lecture notes is by making it a cantilever. So both of them are determinate. Simply supported beam is also a determinate system. Cantilever is also a determinate system. So in this one, that means which degrees of freedom I'm releasing? I am calling them M and R. What I'm releasing here are, you can call it delta I am releasing, or there will be an unknown force R which I am releasing. Okay. Similarly, you can say this theta that is actually supposed to be 0, but I am allowing it to be non-zero by making it a cantilever, or I'm releasing a moment M. Right. So releasing moment M means I'm making M 0 artificially or temporarily. I'm making M and R 0 temporarily. Or in other words, theta and deltas were 0 before, which I am allowing to be non-zero temporarily. Okay. So that has been done now. Resolving the system to a determinate system is done. The third step is solve the determinate system for the external load. I'll call it W. But when I say W, you mean that it's an external load. It cannot always be W. And M, or R rather, and N. Okay. So R and M are both unknown forces, and W is a known force. For all 3 of them, we will solve this system. Okay. So let's do that. So this cantilever, we apply a force W. What is the bending moment diagram? What is if I count X from here, what will be the bending moment at any given X?
Wx square by 2.
Wx square by 2. And if I'm plotting the bending moment on the tension side, where should I plot it?
Up, sir, up.
Up. Okay, fine. So W x square by 2 and plotted on the top. For a moment, I was thinking, oh, it's going to give me a perfect tangent, but later on, it just slipped away. Wait, oh, okay, chalo. Please assume that the beam is only up to here. So X is here. If I try to erase, it will erase the entire line. I cannot erase that small portion. Fine. So this value is W x square by 2. Am I right? Now, whether we call it W x square by 2 or minus W x square by 2 is your call, as long as you are plotting it in the right direction, tension side up, or like being consistent with that, that is okay. So I tend to call this as negative, so I'll keep it negative. So just make sure that if you are calling this negative, then all the plots or all the bending moments that you are plotting upward, you should call them negative in the same problem. Okay. Second part is, actually, instead of doing this here, I should maybe move it down. So that way I'll have more space later on. Okay. I forgot to set up another. Okay. So this is the bending moment diagram for this load. Likewise, for the second one, second case, I'm applying a load R. Okay, and load R is applied upward in the upward direction. So again, this time the bending moment diagram will be at any given distance x. What will be the bending moment at any given x?
R into X.
Okay, I'm counting x from here. So this will be R into x, and this is plotted downward direction because this one will produce tension on the lower side. Again, the third case, this was the second case. This will be the third case. Third case, I am applying a moment. Okay, and because of that moment, again, I am getting tension in the bottom, right? At the bottom fiber. So how much tension will I get at the bottom fiber at any given distance x?
M, sir.
Yes. So it will be M uniform everywhere. Fine. Now the next part is to calculate the I don't like this color. I think it was this one. It was black, maybe. It was black only. Unnecessarily, I was confused. The next step is calculate deflections. Okay, and when I say deflection, I also mean rotations. Calculate deflections, delta, and theta due to the three things. Which three things? W, R, and M. Fine. So because of these three things, we want to calculate how much is the theta and how much is the delta. So if we, what is the method? What could be the easiest method? I mean, here there can be two different methods we can use. We can use the virtual work method, but this is a cantilever problem, right? And for a cantilever, I always prefer which method? For a cantilever, always go for
Moment area.
moment area method. So I will go for a moment area method. The moment area. Okay. So for now, I need to know what will be the deflection, what will be the rotation and deflection at this point. all the restraints are applied here only, right, at this location. So I need to calculate theta and delta at that location only, at this free end. Okay. So I know that if I draw the deformed shape of this beam, which is loaded with W, this was the undeformed shape, then it deforms, it will develop a theta here. Okay. So that theta, I can say, is basically, if I draw the tangent at the fixed support and I draw the tangent here, that theta is the same theta as the rotation at the free end. Okay, and that theta is given by, from the moment area method, is given by area of m by ei curve. Okay, so this is a parabola, and we had just seen the area under this kind of a parabola is 1 by 3 multiplied by the maximum value here, that is W L square by 2. Okay, EI multiplied by L. Okay, and theta direction we have to keep in mind, so it is going to be downward direction, so you can call it negative, because this area was also negative. So you will get, or the values of WL square by 2 was also negative, you will get the minus WL cube by 6 EI. Okay, in this one, for this problem, for the vertical load R acting on this beam, the deformed shape will be like this. Again, the same theta, same concept. So this is the theta I'm trying to calculate. Sorry, it's very difficult to draw it accurately. This is theta, this is this theta. Theta will be equal to, but now the bending moment diagram is triangular, so maximum value is RL. RL divided by EI multiplied by L by 2. Am I correct? Here the theta value will be equal to M multiplied by L divided by EI. Fine. Moving further. Delta. We need to calculate delta also at the free end. How much will be the movement there? So now, for again from the moment area method, wherever we are calculating the movement, if this was the beam and it deformed like so, we draw a tangent at one point. So we draw the tangent at the fixed point. We draw the tangent at the fixed point. That was the undeformed shape, and from there we measure the movement of any point. So we measure this movement. That is our delta, and that is given by the first moment of this area about this point, about the free end. Okay, so basically we just calculated the area, and now we need to do the first moment about the free end. 1 second. So that will be equal to minus W L cube divided by 6 EI. That is the area multiplied by this distance. So this was a parabola. Where was the centroid of this parabola? We just solved it about right. We saw that. The centroid is at 3 by 4L. 3 divided by 4L. So we will say the deflection here, what I'm going to get is W and to the power 4. This 3 will cancel this 6 out. So you'll not cancel completely out. 2 will be remaining. So 8 EI. Okay, that is my delta. Here, the delta will be again, the value here, whatever is written for theta, is basically the area already. So that is this area multiplied by the first moment. The first moment means I have to multiply with the lever arm here. The distance here is, how much is that? 2 by 3L, right? What do I get? 2 and 2 cancels out. R L cube by 3 EI. Likewise, delta here will be ML by EI is the area multiplied by L by 2 is the centroid distance. So I get ML square by 2 EI. Okay? Everybody on board? Any challenges so far? So what we can say is that this theta is because of W, this theta is because of R, and this theta is because of M. Likewise, this delta is because of W, this delta is because of R, and this delta is because of M. Okay? Give me a second, please. Right? Now comes the question of the next step. The next step is step 5. That is basically to enforce the compatibility conditions. Okay. How do we enforce the compatibility conditions? And what do I mean by enforcing the compatibility conditions? See, what we have done here is we had a fixed beam to start with. Correct? Both ends were fixed. Now we had released the other end. That means we made the M and R 0 temporarily in this case, in one case here. We made our M and R, these reactions 0, because we made this end as a free end. So M and R were 0, but our theta and delta became non-zero. And in that way, we were violating the compatibility condition, because for the actual real load, that is W, this is the real load. For W, we got a non-zero theta and a non-zero delta, right? But this delta and theta should be 0. And that's why we have used unknown forces, R and M. So basically what we have to make sure is that delta due to W plus delta due to R plus delta due to M, that is 0. And also theta due to W plus theta due to R plus theta due to M is equal to 0. All this is already given in the lecture notes. I'm just trying to do it on the board so that you don't lose the focus. Fine. So now we can simply write these equations. The first one, that is delta, right? So delta, 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 the three of them added together. What I can do is I can take this W part, delta W, to the right side. So I'll write it in this way. R, first this term I'm writing, R L cube by 3 EI plus M L square by 2 EI is equal to W L to the power 4 divided by 8 EI. The other equation, again, I'll write in the same format. R terms first, R L square by 2 EI, then the M terms, M L by EI is equal to W L cube by 6 EI. Okay. Now what we got is two equations and two unknowns. Okay. This is first equation. What are the unknowns? R and M. What are these? These are forces, right? And because of this, you call it force method of analysis. In addition to flexibility method of analysis, force method of analysis. Why do we call it flexibility method of analysis? We have to just wait. So we got two equations. We need to solve for R and M. Two equations, two unknowns. We can solve it right now. But let's try to write this in the matrix form. Okay. So what we will do is we will take the terms of R and M from both equations separately. What is the first equation going to give me? The first equation will be R multiplied by L cube by 3EI and M multiplied by L square by 2EI. Okay. And that is equal to WL to the power 4 by 8EI. Of course, I can remove the EI terms, but I'm just keeping them so that our understanding of the flexibility matrix is clear. Likewise, here, the second equation I can write, I'll get L square divided by 2EI, and I'll get L divided by EI. And that is equal to WL cube by 6EI. Is everybody okay with this? Looks okay so far, right? So these terms, if you look carefully, what do they represent? They mean basically L cube, this L cube by 3EI, what does it represent? L cube by 3EI was basically your delta R term. R L cube by 3EI was delta R term, which was basically saying, if you apply, if I put R is equal to 1 here, I get L cube by 3EI. That is what you have inside this matrix. So this L cube by 3EI basically means you will get, this term is delta value for R is equal to 1. So if I apply unit R, I'll get this much of delta. Okay, in that direction. Similarly, this one means delta value for M is equal to 1. So if I apply unit moment at that location, I'll get this much of vertical movement. This one basically means theta value for M is equal to 1 plus, R is equal to 1. So if I apply unit R and theta and delta locations, you remember, right? These are all here at the free end. So earlier two terms were saying how much of the vertical movement I am getting here if I apply R is equal to 1 or M is equal to 1. And the second row of that matrix is saying how much of the rotation I am going to get if I am applying a unit R in one case and a unit M in the other case. Okay. And these are nothing but your flexibility terms. Right? These are the deformations for unit force. That is very much the definition of flexibility. So this becomes your flexibility matrix. This one I did not explain. This is basically theta for theta for M is equal to 1. Okay. So this becomes your flexibility matrix. Okay. And you can solve for R and M. So because you are multiplying flexibility matrix with your force vector. So this method can be called force method or the flexibility method. Okay. And then these are the displacements. There are displacements because of the real loads on the determinate system. So this is this method. A couple of observations here. If you see this flexibility matrix, your diagonal terms are equal. These diagonal terms, L square by 2EI, L square by 2EI. What that does mean? It means that this value is equal to this value. We will look at this beam. This was a determinate beam, right? So you had two deformations possible. One is saying this is theta and this is delta, and theta is also having the same degree of freedom as moment, and delta has the same degree of degree of freedom as R. What it is saying, theta due to R is equal to 1 is equal to delta due to M is equal to 1. Okay. Now, if you see carefully, one is a theta, one is a delta. What is the unit of delta? Dimensionally. Is this equation correct dimensionally? Did you follow my question? Gomati, Akshay,
Yes, sir.
does that sound okay to you? That I'm comparing a theta value and I'm saying this because I just simply made a statement that this matrix is symmetric. And if the matrix is symmetric, that means this term is equal to this term.
Yes, sir.
But one of these terms represents a theta value, the other term represents a delta value. Does it make sense?
Yeah.
How?
Like moment.
Yeah. Go ahead. Yeah, what happened?
Yes, sir. I'm.
Harish?
Sir, because
Go ahead.
due to the movement, you calculated the deflection also.
Due to the moment we are calculating the deflection, yes. So, but one value is a deflection, the other value is a rotation. So can we say that whatever the cause may be, but one value is a deflection, how would you write these many millimeters? And this will be written as these many radians or degrees. Is this equation dimensionally correct?
No, sir, that dimensionally incorrect, sir.
How can that be? Then how can I ever say that? Who else? Mohan, Paleti Mohan Krishna.
Yes, sir.
Yeah. No, Shayan.
Sir, it is in means that rotation is in angle and deflection is in millimeters. So both are different.
Yes,
So they, according to me, they cannot be equal, sir.
they cannot be equal. Krishna Katyal.
So, I'm not getting
You're not getting the question or you're not getting the answer?
the answer.
Not getting either, huh?
Not getting the
Did you follow?
answer.
Not getting the answer. Okay. Okay. Vishal?
Yeah, yes, sir.
Yeah. Want to guess?
So my theta for r is coming out to be L square by 2EI, and my deflection for m is coming out to be uh, I mean, so actually, sir, it depends on the R is unit is kilonewton only, so
Very
it is
good.
L square, and m unit is kilonewton meter, so it will be only L.
Correct. Yeah, I mean, so basically that is, thank you, Vishal. Very good. So these are not theta and deltas actually. This is a trick question, but it is important to have that clarity. So what it is actually is theta by r, and what this actually is delta by m. Okay, these are not theta and deltas, because when I'm saying r is equal to 1 and m is equal to 1, automatically I'm saying it is theta for a unit r, delta for a unit m. And now these are dimensionally correct. Fine, because anyway we are going to multiply these values with r and m respectively before we equate them. Fine. So now this is dimensionally correct. It is radians per kilonewton, and this is basically millimeter per kilonewton meter, or like, oh sorry, I should not use kilonewton here. Be consistent with this thing. Meter per Newton meter. So this will be cancelling each other out. So radians is again unitless. 1 by Newton on both sides. Fine, makes sense. I hope that answers the question. Okay, so now we can solve this equation, and we will quickly show you. So you can solve this to calculate R. R turns out to be W L divided by 2, and M turns out to be minus W L square by 12. that correct? Yes. Okay. So since m value is negative, what it means is that, see, r value is positive. That means this reaction, external reaction, was in this direction. But m value I had assumed to be counterclockwise. But what I got for m is a negative value. That yes. So what it means is that in this beam, my r is this much, w L by 2, and moment is actually not counterclockwise, but it is clockwise direction, w L square by 12. And then there is this load acting. Okay, that is w. And on the other end, also you can solve. You will get, how will you solve it? So you get the reaction, this reaction, R1 you can call it, for the three cases: when the W was acting, the second case when WL by 2 R was acting, and the third case when M was acting. And substitute these values in the respective cases, then you will get this value. So this will be WL by 2, and this will also be WL square by 12. And then all you can do is simply, if you want to develop the bending moment diagram, the complete bending moment diagram, I had one bending moment diagram that was this way. Okay, that stays. Plus then I had another bending moment diagram which was this way, right? This value was R times L. Okay. I'm just marking the direction. And then the third one was M here. So if I substitute the value of M here, so at any given point, this value was Wx square by 2, right? Am I right? This value was R times X, and this value was M. So the total moment will be Wx square by 2 minus, because this is in the opposite direction, this is positive, or otherwise I'll keep it negative, minus Wx square by 2 because this is negative, plus R value I'll substitute. In this, I will substitute the R value. So that is WL by 2 X plus M value is WL square by 2. But that is also negative, right? Because I had assumed M to be acting in the counterclockwise direction, but this is actually clockwise direction, minus WL square by 12 multiplied by moment. Okay, so this will be the generic equation for that bending moment diagram. You can plot it. Please let me know if I made a mistake here in this calculation. Please recheck this calculation. Okay. This value will turn out to be WL square by 24, and this one will be minus WL square by 12. Fine. Everybody looks okay?
Yes, sir.
Yes, sir.
All right, fine. So now, just to bring home that point again, that the flexibility matrix is symmetric also implies one more important, there is a theorem basically, it is called Maxwell's theorem of reciprocal displacements. And that is basically just an implication of your flexibility matrix being symmetric. Okay. And basically all it says is that if you have any system, if the system is linearly elastic, you apply a unit load at one point and measure the displacement at any other point. Okay. And then you apply a unit load at that other point and measure the deflection at the first point. The two deflections, that is FBA, that is deflection at B because of unit load at A, will be equal to FAB, that is deflection at A because of a unit load at B. Okay. So this can be often used when in conditions where you cannot measure certain displacements. So you can, or if you don't want to repeat the work, you can simply use this. Okay. And for this, another advantage in this particular method is that you don't have to solve the entire flexibility matrix. If you know that you are doing it right, you can just solve half of it, and the remaining half you can assume to be correct. Or otherwise, you can solve the entire flexibility matrix, and you can again match whether your non-diagonal terms are coming out to be equal or not. Okay, so that the stiffness terms are to be symmetric. The matrix terms are to be symmetric. Fine. Okay, one more example I wanted to do, but this example will take some time. I don't know whether I will definitely not have sufficient time to solve this example completely. How much time do I have? 12, 11 already. I think I'll skip that step. I'll take some questions if you have any. And in the next class, we will do 2 examples. We will go a little bit faster and try to cover both examples in the next class. Okay. Any questions, fellows? No questions. Huh? All right then. We'll see you in the next class. Monday, right?
Yes, sir.
Okay then. We'll see you on Monday. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.